Bismillahirrahmanirrahim. The topic of my research paper is P versus NP problem. First, we describe the abstract of my research paper. The success of our computers has often led to some interpretation. We have the technology venture driven by search for better physical material and devices that can be used to build smaller, faster, and quicker computers. Uh, then we use the search for efficient algorithms or programs or software depending on the reader's preference. So here we will introduce to the best very basic element of the theory of computing. Start with the elementary examples. First one is Turing's contribution in the 1930s that led to the development of both computers as theory of computers. We will use the efficient computing from 1970s, leading to the question that if E is equal to NP. We will explain this question, its significance, and its important consequences of its resolution depending how the question is resolved. The introduction of this research paper is the discovery of about computation is the essence of Turing's contribution to the science of computing, popular as universal computer. The work in mathematical logic at the point had been discussing what a theorem is and what are the proofs are, and how quickly these theorems can run, and what are the complexities of these problems. Really, it is a really fundamental notion. In this article, we will describe it. So here we discuss some examples from high-level description of computing. That is, what is computational problem and what does a solution to a problem known as an algorithm look like. We have the addition property. We use the two integers to add them, and then we have the multiplication property, the product of x and y, and then to the power 10 to the power n minus 1, the required result, and it would have the 100 billion steps or 100 steps. All these explanations are discussed in the slides. So another one is factoring, where the polynomial time, the big theta of n, or n to the theta of n to the power 10. Then we have the divisor problem example. We will describe the NP complete problem. So what is the solutions to a polynomial time system? These are how quickly it can be solved. The Fermat's last theorem, which considers the following equation: the x to the power n plus y to the power n minus z to the power n is equal to 0. Similarly, we have the values of n is equal to 2, x is equal to 3, y is equal to 4, and z is equal to 5. And we would describe these one, and some computer scientists tried Poonian and Matthew give the these equations. We will discuss in the slides. So we will describe some computational complexity which has the formality. We have 5 steps. The first step is an algorithm should be finitely described. At the same time, it should be capable dealing with infinitely many possible inputs and produce many outputs. It should be allowed to use scratch paper, and the 4th point is its actions at any point of time may depend on the past. And the 5th one is it should model every physical realizable computational problem. The first 4 points are restrict and limit to the action of an algorithm, and the 5th one is the expensive in its design. So in the rest of this section, describe technical formalism that Turing imposed for his notion of an algorithm which manages to satisfy 1 to the 4 items or steps, and seems also satisfy 5 modulo detail of the law of physics. Then the Turing's formalism, we have the 6 tuple q epsilon, we have epsilon, q naught, and f, and the sigma, where q is the finite set describing set of states control can be. Sigma is a finite set describing the set of letters. Q naught, f belongs to q, are the initial stages or final stages or halting stages, uh, the special symbol, and then the sigma q cross e um, summation, and q cross summation x. These values are +1, 0, and -1 is the state transition. We have the head and the tape on the both of the sides. So Turing's formalism is finite state control and infinite state and the head. So different algorithms can solve this. So we have the implications of formal definition that serves Turing thesis. Every physical realizable computation can be simulated on a Turing machine. We will remark on the challenges brought up with randomness and quantum physics later. So the implications of formal definitions have the computational complexities. The formal definition of an algorithm is helpful in the design of an algorithm but is not essential. So the polynomial equation, does it has a zero among the integers? This question is also undecidable, that is unsolvable by any algorithm. Then we have the polynomial and exponential time complexities, two very broad classes, that polynomial time computable problems. These are also known as exponential time computational problems. These have the theta of nc or some constant c independent of the size n. We solved this by in time to the theta of n to the power c for constant c. So many classes of problems, polynomial time running time often offers a clever alternative or an insightful solution for brute force exponential time solution. The problem P versus NP question, the map coloring, the travel salesman problem, and the shortest supersequence problem, the all of these problems are factoring and divisor share some common features. In each case, there is an underline clarifies the question whether it is true or false, or easy verification procedures, and finally the question what is the is P is equal to NP or not. So the NP complete problem are possibly the highlight of NP. They come in a variety of contexts and seem to reflect very disparate aspects of mathematical or human case. So the P versus NP problem has a self-decision equivalence implies to the solution of the problem, and having the divide and conquer approach if we solve the problem in three coloring or three colorable, we using the map coloring or travel salesman problem as we discussed in the slides. So finally, the optimization of this is the verifiability or the most optimized solution we will give to the algorithm. This is polynomial time or NP complete is verifiable or not. So we have the logics and mathematics used in this. The foundation of mathematics is the formal logic and consists of some explanations may be true or false and derivation rules explain how a collection of assertions. So if P is equal to NP, then one could have an automated procedure replacing the creativity mathematicians finding proofs of theorem. This is of course feels very counterintuitive, adding to the general belief that perhaps P may not be equal to NP and mathematicians can't be replaced by computers after all. So finally we have the conclusions. We conclude that computing is not just a study of what computers do or cannot do or can do. It is a much broader study of logical reasoning entirely and offers the foundational framework for a wide variety of human activities. The example of addition and multiplication show highlight the compute all the time or may get the intelligent results or good results, which results should be thought as natural laws that we cannot afford to overlook. Of course, the science of computing remains intimately connected to the practice of computing, and as computers become more powerful, more interconnected, and more capable of controlling mechanical devices and more ambitious in their attempt to communicate with humans. The nature of science is also changing with it. The modern theory of interacting computers sees many more laws than just irreversibility of energy completeness. It should be safe to assume that the course of 21st century will be dictated to a large extent by new paths that the science and technology take. So that's all the final conclusion we will describe to you, and we will hope by way of representation this research paper is understand to you. Thank you and Allah Hafiz.